Thanks, Darren, and thanks everyone for your time. What I'm going to do today is share with you some a real interest of mine, and that is on statistical power analyses. And before we do something here, let me just do that. As well as effect sizes. Many years ago, I taught this created and taught this interpretation of data class at another institution before Hahnemann/Drexel. And that was the where I started really working more intensely in terms of the statistical power analyses and effect sizes. So one of the things that comes to mind is that we really need to consider how we can address what sample size do we need and what's the lowest meaningful effect for a study. And so we're going to look at a few different topics today to that end. So there are 5 areas that we'll consider: interrelated factors that are involved in statistical power analysis, null hypothesis, statistical testing, and types of errors. So we're not even going down the Bayesian route. It's just staying frequentist. Looking at different types of power analyses, also considering effect size categories, and different examples of power analyses using some software, G-Power and R, which is all freeware. So you could really address what's happening in terms of a power analysis for various studies, and it's not going to break your budget because you'll just have to put in a little bit of time to learn the software. So one of the points in terms of significance, in statistically significant does not mean necessarily that it is important. Okay, this is a little cartoon help things as to Shakespearean. So the probability of audience uproar is always high for Shakespeare night at the Statistical Society. And one of the things that keep in mind is in Shakespeare day, when we consider what's happening in terms of signify, that meant just something, not necessarily importance. And in a statistical instructional article, and also was more involved in terms of nature, Rachel Nuzzo explains that the developers of the test last century, so 100 years ago, where a p-value less than 0.05 was signified as worth studying further. We've seen how the world has evolved in terms of this p is less than 0.05 and what's happening in terms of significance levels and the impact it has in terms of research. So we really need to start considering 2 different types of significance. One is we're looking at this p-value. P-value just tells us if this is reliably different from chance or not based on the threshold that we've set. As well, oh, sorry about that. The other would be the effect size. The effect size is a measure of clinical significance, of practical significance. It adds meaning to the information. And you have seen since the 1990s when Wilkerson, the task force with APA, and it's also been done in a variety of other areas, there's a real focus on including effect sizes in a study so that you can help place the information into context. So one of the important points that we want to consider with respect to doing power analyses is to look at this one simple formula. So ES represents effect sizes that are estimated. TS represents a test statistic, and some function of n would represent our sample size or degrees of freedom. And so we can see in an independent samples t-test, we have the effect size, variances, sample sizes, and what we're having in terms of our null hypothesis, which we assume is 0. So the effect size, we consider one of the methods, which is the difference between the means. We know that the variance is going to have an impact in terms of the output. And then we also consider the sample sizes of the groups. So this variance, this is the standard deviation pooled in this sense. So if we did have differences in terms of the sample size, we would be able to address that. And we'll take a look at one of the basic formulas with that in a second. So we have two hypotheses. I just created some data, and I'm going to move this down. So our null hypothesis is, well, what's happening in terms of some simulated data of weights between females and males. And we see the gray box with the line, the dotted line representing the mean, which is 144 pounds, and with the simulated data of 200 cases, and then the males, another 200 cases, and that's 175 pounds. And so our null would be the population weights for males is equal to that of females, whereas the alternative hypothesis is that they're not the same. And so we could look at these pieces of information, these density plots, which give us a sense as to, well, where's alpha, where's beta, so as we'll look at in a few minutes. But that gives you a sense as to, well, what's happening in terms of our effect sizes, these differences, the n that we have, and then also what's happening in terms of the test statistic. If we have more variance, we have an increase in terms of the variance, that's going to have an impact when we compare our calculated test statistic to what's happening to the table test statistic. Let's look at some interrelated factors that are involved in power analyses. So we see that statistical power, alpha, sample size, and some effect size index. We have two of these. We've held another one constant, and we can see what's happening in the relationship of the other variable between these four. So if we are interested in determining a priori power, we'll find we set the alpha. We'll determine what's the lowest meaningful effect, and then we'll look at the relationship between power and sample size. We'll also consider, well, what role that variability plays in this whole process. If we have higher variability, that's going to impact what's happening in terms of sample size and the power. It will also impact our effect size. Right. What is statistical power? There's a variety of different definitions. Cohen, from his seminal work and many texts that have been noted, we're looking at it as the probability of making a correct decision. So if we consider what's happening with the two graphs that are located to the right, we have the critical t-value. We look at the standard mu in terms of 0, 1 standard deviation. We have alpha representing our type 1 error, beta, we have this critical t, and here we have what's happening in terms of, let's say, our control group. And then shifted to the right, we have what's happening with the experimental or the intervention group. And then we note that this gray blue dotted area represents statistical power. So again, we have this as the probability of making the correct decision, or the probability of correctly rejecting the null hypothesis. Now we know in terms of statistics, there are errors, and we will discuss some of those errors shortly. How sensitive a test is indicates again, what's happening in terms of the probability of us making the correct decision. So we want to have a more sensitive test than a less sensitive test. And then we also consider power as the probability of correctly detecting an effect. In terms of significance criterion, this is alpha. See it represented as significance criterion. Cohen noted the smaller value is a more rigorous standard of null hypothesis rejection. So moving from the 0.05 to 0.01. If we assume whatever we're studying that the phenomena exists, then a more stringent significance level is used. And then one of the points we could have with that is perhaps we have an increased sample size as well. We could note, well, this is the risk that we're willing to take, saying that a difference exists between the groups when in fact there is no difference between the groups, or an association is apparent when in fact there is no association between our measures. In terms of sample size, let's look at what's happening in term here, and we could do this a priori. We have our interrelated components set. So we set alpha a priori. It's not done after the fact. We also know the effect size that we want to detect, and also how much power that we want to have in this analysis so that the probability of making a correct decision is increased. Typically, we're seeing that 0.80 or higher is the sufficient level of power. Another point that we want to consider is that we want to be economical, we want to be efficient. So you don't want to have too much power, you don't want to have too little power. And in this respect, you want to be able to have a sense, and we'll take a look at this in terms of, well, what's happening with the lowest meaningful effect that I can detect? Right. So we know the law of large numbers, increase the numbers. Yeah, you'll find a statistically significant effect, but is it meaningful? And that is the question. Is it clinically meaningful? Is it the minimal clinically important difference? Is it practically meaningful? How does it fit in the realm of studies that have been done? Another interdependent factor is that of effect size. So we look at this, is our phenomena present in the population? What happens in terms of the use of metric-free or standardized mean differences in terms of power tables, which is one form of an effect size. And we could transform between the different effect sizes. The question that underlies our work in terms of conducting power analyses with effect sizes, how large an effect do I expect in the population? And we'll take a look at this in a way in terms of applying confidence intervals. So in calculating effect sizes, we're looking at a group contrast, and we consider this for the most part continuous. We use a pooled standard deviation. So if you recall from the t-test formula before, and here we see Cohen's d, so our estimated effect size, if we take the difference between two groups, and then it's divided by the pooled standard deviation. And here we need to consider two cases. One, if our n is equal, then it's simply the variance of group 1, the variance of group 2 divided by 2, and we take the square root of that region. Otherwise, we need to do a weighting, and this weighting involves removing a degree of freedom for each of the groups, and then you also have your degrees of freedom from the t-test in the denominator. So we would take the square root of those values. And that will give us a more accurate standard deviation pool than would if we use the n1 equals n2 when we don't have equal n. And there are many situations when we do see this unequal n, especially for the different t-tests that are used. One of the areas that makes a big impact in terms of our work is how reliable is our data. And the reliability of the sample refers to precision. And we consider the precision as the standard error of the mean, which is the standard deviation of the variance divided by n, and then we'll take the square root of that function. And this gives us how close are the results to the population. So how much error is in this data? And this tells us how reliable. A higher standard error of the mean relative to the data that you're collecting, then it's not going to be as reliable in terms of results. And we see that happen in many instances. So bottom line is increase sample size, you'll increase your reliability of the data and also reduce error. Again, we still need to juxtapose how economical, how efficient, what happens in terms of the increased sample size. Do I have enough funding for this sample size? Do I need to make some other decisions relative to sample size to try and control some of these other factors like the effect size, and we'll also look at some other types of power. Another point that is critical is looking at these different distributions. And the different distributions will have the central distribution as well as the non-central distribution. The non-central distribution gives us information in terms of power. When we compare this to the central distribution, we'll look at also the type 2 error, which is beta and alpha. And we'll also note that for this non-centrality parameter, you'll see this in terms, especially in G-power in some of the outputs. So it's like, this non-centrality parameter. Well, it's going to be used in our sample size and power calculations. What it means is how much can we rely on the null hypothesis being false? And we'll see that it's available for t-test or t distributions. So we have the effect size and our sample size. This helps us in terms of the non-centrality parameter to invoke our sample size calculations. We see this in terms of an ANOVA model or the F ratio and the effect size omega squared. And as well, we look at this in terms of omega or Cohen's W, if you will, for the chi-square distributions. The other piece to think about with power analysis, is if we use confidence intervals, some will refer to confidence intervals as a precision analysis. And you'll see this especially in terms of meta-analyses. With precision analyses, in terms of confidence intervals, the narrower the confidence intervals, the greater the statistical power. So some basics in terms of confidence intervals, we look at the test statistic, the standard error, the width of the confidence interval, and then if you think of it conceptually, it's our point estimate plus or minus the margin of error. And we'll be using confidence intervals to determine the lowest meaningful effect. Let's consider then null hypothesis statistical testing and some types of errors. So very familiar with the confusion matrix or the truth table. And we can also see how this is graphically depicted to the right, where we're considering our our control group or null hypothesis, which would represent it with a red line and then in distribution. And then we also see the dotted blue line, which represents the experimental or intervention group. So we're looking at what's happening with truth or reality as a function of the data or based on the statistical results. We could have a situation which is a type 1 error, and where we're saying, again, that there is a difference when in fact there isn't. We could have type 2 errors saying that there is no difference when in fact there isn't a difference. And then we'll consider two different types of correct decisions. This particular box of correct decision 1 minus alpha, the null hypothesis is true, you fail to reject it, you need to control more of your methodological components in terms of your study, because it's a correct decision, but you used an awful lot of resources without much benefit. And then we have the other correct decision, which is 1 minus beta, and that is our statistical power. So this is directly linked then to what's happening in terms of our distribution. So in that, we could look at a couple of types of errors. The type 1 error, a false positive. Type 2 error, a false negative. Obviously, we could see those differences. And I wanted to introduce you to another type of error, and that is a type 3 error. A type 3 error, this is noted by Mendes, and the type 3 error is when you are doing a directional test and you incorrectly interpret your test. And so if you have a test where your one group should be greater than another group, and you see that it's close, well, that is adding another type of error in this type 3 error in the mix. There's also a type 4 error, but we won't go there. So in this, we see this type 3 error, which is gamma. And so to really get a sense in terms of power, Mendes argued that we should go and calculate 1 minus beta minus gamma in terms of these wrong decisions. So all of these errors, we want to eliminate the error, so we have this probability of making a correct decision. I'm presenting this graph from, and it's from Wikipedia, in terms of some of the errors, just to get a sense as to the diagnostic 2x2 table. So looking at our true positives, our false negatives, our false positives, and the true negatives, and how they're related to the distributions and testing. As well, what we see is what's happening in terms of the sensitivity, which is on the y-axis. And as we see an increase in terms of sensitivity as a function of specificity, we note that we'll also see more in terms of this increase in power. And so they are related. We will see these applications being made. Let's take a look at some different types of power analyses. So this is a graph from G-Power. And you see the interdependent factors. This is an example of one type of power analysis, which is a compromised power analysis. And you're seeing, well, is it a directional or non-directional test, the effect size, we'll look at something called the beta alpha ratio, the sample sizes in the groups, and then the power. You're also seeing the noncentrality parameter and some of the differences that we'd note in terms of alpha and beta. So our a priori analysis, we're estimating our sample size to reach a level of power. You're most familiar with this type of power analyses. We'll also look at post hoc analysis, and that's for giving us a sense of power when we have the data that's already collected. Compromise power analyses, one of the issues that come into play is, let's say your resources are limited, which we all know that happens very frequently, and you can't get the number of cases that you need. And so with that, you'll be able to get a sense as to a compromise power analysis when you assess the risk between a type 2 to type 1 error, and this is the Q ratio. So how risky is it to make a type 2 error relative to a type 1 error in the work that you're studying? An a priori power analysis, again, we're estimating the sample size before conducting the study, and we can see what's happening in terms of the output. We also want to keep in mind the question, what sample size will I need to have sufficient power to detect a minimal meaningful effect? What do I need? I control the power before the study begins, where n of these interdependent factors is a function of power, alpha, and our population effect size. Another power analysis is that of post hoc power analysis. And we're estimating the power after a study is conducted or published. Okay, so we have the sample sizes that were apparent in the group. The effect size, this is the critical variable that we're concerned with. And the reason I mentioned that point is that we're going to take a look at, well, what power did I have to detect the lowest meaningful population effect size? If you simply take the effect size that was calculated with the data, that does not represent the lowest meaningful population effect size. You think of the central limit theorem, you'll note you're not going to get that same effect size. So you want to be able to make sure that you don't use the effect size that was calculated. That's referred to as retrospective power. And it is a false assumption. There's a good deal of work out there addressing the problems that are inherent with this. I mention this point because if you are asked, reviewer asks, well, what was the power of the study? You really want to go through and estimate the lowest meaningful effect and calculate what the power was for the lowest meaningful effect in terms of a post hoc power analysis. And you could go and identify, well, retrospectively, with this particular effect size, yeah, it's likely we probably didn't get a significant effect. However, to do a replication study, I would increase sample size to a particular level, whatever was needed based on the lowest meaningful population effect size. Right. Now, the other effect size, power analysis is this of compromised power analysis. And with compromised power analysis, we're going to estimate the sample size before conducting the study. It can be calculated, we know, before, and we don't have to exceed any available resources. It can be conducted after, and the data aren't analyzed, but the reasonable decisions are being developed. So we see that alpha and power are a result of the effect size and the error probability, which is Q. So type 2 error and type 1 error. If you look at what's happening in terms of the Q for a typical study that saying, oh, well, I need go for probability of 80% power, and alpha is 0.05. If you look at that, beta, which is 1 minus power is 1 minus beta, so beta is equal to 0.20 divided by 0.05. So we have this 4 ratio. And I just put a graph here from G-power. So as we consider what's happening with power, and power are the numbers inside these plots, and we see the different effect sizes. So 0.25, 0.4, and then 0.55. And if we consider, well, what's happening with this low effect size, it's not going to work. All right. And then we consider we still have insufficient power with an effect size of 0.4. We do have sufficient power when we have an effect size of 0.55. So we need to consider what's happening with the effect size within these various studies. And then also do an a priori analysis. If you have, if the sample size is something that is unattainable, then consider doing a compromised power analysis. So in our compromised power analysis, we have the type 2 error as a function of type 1 error. And we'll also note that we could do some manipulations with the beta alpha ratio, and you could get an estimate in terms of power. I use the same values across many of the different examples initially in identifying these power analyses to show what's happening in terms of compromised power analysis, post-hoc power analysis, a priori power analysis, and the information that you input into G-power. Another power analysis is sensitivity power analysis. And this will be able to detect, asking, well, what power can I detect given its N and alpha as specified by the authors? So we have some information. What was the minimal effect size to which the test was sensitive? We could evaluate published research, looking at, well, what's happening in terms of our effect size with power, alpha, and N. So we have our power, 0.8, two-tailed test, 0.05, and we have 64 in each group, and the effect size that we would need is essentially a 0.5. And so that 0.5 we saw in the other examples also. So it's really a nice way to check. This is another technique to use as to evaluating the work that you've already done prior to doing a follow-on a priori analysis do a sensitivity analysis instead of a post-hoc analysis. So keep those methods in mind. Let's take a look at some effect size categories. And we're going to see that we have mean differences, so or D or G and delta. We have strength of association, some examples, correlation coefficient, partial correlation coefficient, multiple regression correlation coefficient, our regression coefficient, beta, rho, and then tau. We could look at corrected estimates, which are the proportion of variance explained, eta squared, omega squared, epsilon squared, and the R squared adjusted. And then we have another category in terms of the risk estimates. So in these effect size categories, one of the things that could happen is we could make transformations to say, well, I want to find out what an R is from a D. I'd like to know what an odds ratio is from a D. And you can make those transformations. Right? One of the areas to consider for identifying the lowest meaningful effect is if this is the point estimate that you calculated in terms of D, it's likely that if you repeated the study, the effect size could be lower than that point estimate, could be greater than the point estimate. What you want to do is to be able to hedge your bets. So if it's something that's possible, calculate the effect size, confidence interval, and go closer to this lower limit of the lowest meaningful effect, because then you have just an increased area in terms of making a wrong decision. So if it's not prohibitive, go closer to this lower limit. If it's going to be prohibitive in some way in terms of your resources, then move closer to your point estimate, knowing that you might have these different errors coming into play. There's an article that's out from 2002, and this is an amazing article in terms of looking at clinical importance and the minimal clinically important difference and the categories. And what you do is to look at, well, what's happening in terms of the minimally clinically important difference, so the MCID, which is represented by this X. The line that you see here is the 0 line in terms of statistical significance. So you could then note, well, is it benefits or harms? And you could look at what occurs relative to the MCID is below the lower limit of the confidence interval. So we would have clinical importance, also statistical significance, because it is above this line. So for all of these different combinations, so probable, we see where the MCID is relative to the confidence interval, and then also to the 0 line, and whether it would be statistically significant or not. So we could have situations where our data is not statistically significant, but it is probably clinically significant. And then we could have the possible scenario, and we look at what's happening in terms of the confidence interval and the width and the location of the MCID. And then definitely not. So we have quite a bit of type 1 error here. Our MCID is above the upper limit of the confidence interval. So I'd ask you to consider thinking about this article, and then look in your area of interest. It might be a nice application to really understand what's happening in the literature in your area. So we have these 4. Another example is this by Roby, and there are 7 different levels, similar, but presented in a different way. We have the minimal important effect, and we'll say it's 0.8. You have your confidence intervals, and then you also have the effect size of 0, which would give us a significance region. So you could tell whether or not it's clinically important as well as statistically significant. Created this table to address what's happening with several different areas. So it's Cohen, Rosenthal, and Shewokis. Shewokis went and said, with standardized mean differences, it did some simulations, said, may need to look at what's happening in terms of some very small or very weak effects, as well as huge and extremely huge effects, which extends the 3 areas which were previously referred to by some individuals as the Cohen's t-shirt method. So do I have a small effect? Do I have a medium, large effect? Now I guess we could call, if it was a t-shirt effect, an XL and double XL or something along those lines. In any case, you see these measures, you see these values now extending to a different region. I have some open sections because there was nothing reported. Could guess as to what it may be, but I'd really like to do some simulations to test it. If we consider strength of association, here are these the correlational values, and we have differences in terms of the interpretation of them. Having risk estimates So 1.5 to 1 or 1 to 1.5. So depending upon what you have for your odds ratio or the risk estimates. And you see the ranges. And then sometimes there are percentage differences that are used between one group and another. And we will also note that here are the points that you would expect given the range of 15 to 85. So we've extended the rules of thumb well beyond this small, medium, and large section that was previously used. And really it was focusing on, for the most part, small, medium, and large standardized mean differences and strengths of association. Right. So what I'm going to do is show you some power analyses, and there's also a site in terms of visualizations. The visualizations, I'm not going to go there because I'm just checking what's happening in terms of the time, but we'll step back if there and do so if there is enough time. This visualization, you could go through, look at what's happening, the relationship between alpha and beta for different values, what's happening in terms of power analyses, what happens when you change Cohen's d. So I will be providing the slides later after, and you could check that out, or you could just take a look at this now and or after the presentation and see if there's anything that's helpful for you in terms of getting a handle on the concepts. Software we could go to is G-Power is the link, which I have here, as well as R and RStudio. And in R, look at a couple of effect size packages as well as some power analyses. So let's take a look at the first example. I went into R and used the power to PWR to PPL, which is Aberson. It's one of the authors that I use in RSCH 812. So it refers to power to the people package. And so I created this fictitious data, thinking, okay, it's in the afternoon, maybe someone is interested in chocolate. So let's say, what's the effect of different types of chocolate on systolic blood pressure? So we have one group which has an N of 30. Their systolic blood pressure was 124. Let's say they were randomly selected, and similarly for the dark chocolate group, and the standard deviation is 8. And then the dark chocolate 38, but their systolic blood pressure is 118. Well, you'd use this code in R, which is INDT for this package, and the mean of group 1, mean of group 2, the 2 standard deviations, the 2 N's. And in this package, you'd get, well, what's happening in terms of the D, which is 0.75, and you get the equal variance power. And if you had unequal variances, you would get power also calculated. Little different in terms of G-power. In G-power, you'd input the effect size. You could calculate the effect size by clicking on determine. And looking, we have equal N's, mean of group 1, mean of group 2, or standard deviations, and then it calculates the effect size. You can also transfer. Your error probability, the sample sizes in each group, and then we have the power, critical T, and the non-centrality parameter. Right. So those are calculations that can be done. We'll also note, well, can I check power in another way with R? But look at the power PWR package. You see there's slightly different input. You have the code input, and then you could calculate what's happening in terms of power. If you like more of a GUI interface, you might want to go with the G-power. It doesn't involve as much in terms of the the coding at this time. Also, we consider what's happening in terms of the output. So if you said power is 0.8, then we'd need 29 cases in each group for the milk chocolate and dark chocolate. If we did the 0.185, which we noted was what we found in terms of the G power and the PWR2 PPL output, we'd see that it's the 30 cases in each group. What I also wanted to do was to calculate the what was the T value, because we could look at some different effect size indices calculations and packages. So I went and I found another package and just did the t-test using the means and standard deviation. So I input that information and I got the modified Welsh two-sample t-test. So we have our t, which with 58 degrees of freedom is equal to 2.905. You could go 04 if you want to be a little bit more conservative. So you truncate rather than round. And the p is equal to 0.005. We have our 95% confidence interval in terms of alternative hypotheses, and then we see what's happening in terms of the sample estimates. What's nice about this R-compute effect size output, I input the test, the t-test, and the two values. So you get the D, you get the 95% confidence interval for D. The p-value, you get some other, the U3, the CLS, the Cliffs delta, or some other effect size indices. Right. You also have Hedges G with the confidence interval, correlation effect sizes, confidence intervals, Z and confidence intervals, the odds ratio, the log odds, the number needed to treat, and your total N. So you get an incredible amount of information, and it saves you a good deal of time rather than working through some other means to go and do transformations. So with that, I'd like to thank you. And wanted to note, if you have any questions, any insights, this is Argent. He's my stat cat, and he's getting itchy. He'd like to take over the laptop. That's one of his favorite spots. If you're interested, they have RSCH 812, which is offered online with also synchronous meetings weekly in the spring. Thank you.
Thank you, Trish. That was amazing. You gave us tons of information. I'm glad we recorded it so that I can listen to it again. Are there any questions? This was really amazing, especially right now when sample sizes are small. So trying to figure out how to statistically look at a small sample size, this was incredible. Thank you so much for this information.
Sure.
Any questions for Trish?
So this is more of a broader question in thinking about study design. So this was for hypothesis testing.
Mm-hmm.
Is power analysis relevant in any other type of study? Like, how do you make sample size determinations on, say, more descriptive studies?
Descriptive studies, that's if you're considering feasibility studies, pilot studies, that's one aspect. If it's much more descriptive, you could also make applications, Elise, with any type of statistic. So your binomial, your proportions, your what might happen in terms of frequencies. So we look at regression models, these other areas. There's a whole set of other analyses which are single case designs, right? And those may be included more and more these days because of the fact that there are various restrictions that are in play. There's also the whole Bayesian perspective. So if you're thinking more along the lines of a mixed methods type of approach that is really more in terms of the just descriptive. At this time, I'm really not sure.
Yeah, no, I meant more in terms of what you're saying. So you have hypothesis testing, but let's say you wanted to do more of a regression, but you're just trying to sort of get a sense of, or like a clustering analysis or something more along those lines.
Any statistic you can,
Okay.
And really any statistic you can. It's a matter of determining, well, what's the critical beta coefficient? What's your critical comparison that you're going to be making? And then getting a good estimate of what the effect size index might be. And so if you think back to the effect size categories, it may be the strength of association, it may be the corrected association, it may be what's happening in terms of odds ratios. Something that makes sense for the hypothesis and research question that you're testing, as well as making sense to the journal, the audience, the grant that you're applying. So those have to connect really well. Otherwise, you could put a power analysis in, and if you're limited by space and not explaining very much, sometimes it might do you more harm than good. It's unfortunate, but that's the case.
I unfortunately have had that happen on a grant, right? Yeah. If you don't have enough space to describe it in full detail, it actually did me way more harm than it did me any good. It was specifically pointed out as a major flaw. So yeah, thank you for saying that. That's very true. Anything else?
Yeah. Hi, Trish.
Hey, Bob.
Question, your perspective. So what really struck me in listening is thinking about reading articles and how people, when they report, a lot of times it's a priori reporting their effect size. Here's how we decided we needed 60 in each group. What I found interesting is oftentimes people will look at an article, right? A study that might have used a measure, and they'll look at what the post hoc effect was of that.
Mm-hmm.
And then they'll use that as an estimate of the effect size. And then from that sort of work towards, okay, here's the sample size. And I think it struck me as that may be very simplistic and not necessarily an indicator of the population effects. So I didn't know if you had any thoughts or ways that you might go about looking at that with a little bit more insight or a little bit more carefully than that.
Well, I think what you're describing, Bob, is the retrospective power. So
Yes.
You're using that effect that was detected and saying, oh, this is what we detected. That's the population effect. And it's not. They're not equal. Let me pull up. So that's one point. So you would go and determine the lowest meaningful effect. You can do that through the sample size, but there's also another point that I'd like to raise, and that is okay. I think it's Pellegrini and others have come up with this safeguard power analysis, and they make the use of safeguard power analysis to replicate a study, to explore different scenarios.
Dr. Shewokis, are you trying to show us something? Because we just see your face.
Oh, I'm sorry. Yeah, I forgot the share screen. Apologies.
No worries.
So this might work. Sorry, folks. The safeguard power analyses. So there are 3 recommended uses: replicating, exploring different scenarios, this might come into play, and as well as evaluating empirical evidence. And so it goes on to indicate how to do this. And let me show you the next slide. So this is from that article, and all of the articles are noted in the references. So it's, let's say that the effect size of the original study was 0.7, and then the sample size of the original study was 50. Well, the effect size considered for safeguard power at an 80% level of protection, which is an 80% confidence interval.
Yeah.
And then the sample size computed using standard power analyses. Then the sample size considered for safeguard power analyses at this 80 level protection, right? And then the 2.5 times rule, and then the safeguard sample ratio. So these are, so then you start looking at it, well, I have the same, the next example, the same sample size, the same effect size, a higher sample size. What happens here? And you see this dramatic difference and change. Then when you have a larger sample size, a larger effect, larger sample size, the smaller sample size, and you see these changes. So those are considerations that we'd be able to make, and we can, I think this is, again, another area to start really addressing. I'm also looking into the pilot and feasibility studies in terms of power analyses. And there's some arguments who say, no, they're not good for a power analysis. And others will say, indeed, you need this, or just even to get estimates. So there are ways that you could go in and show variability in your data. So with your plots, do the jittering, show all of the dots. That makes a big difference, more so than just saying, oh, we did this to calculate the reliability, the variability, and this is the standard deviation. It's not enough anymore. Graphs are really needed, because then you could see, is this an outlier or not on these pieces.
Thanks. That's informative.
Wonderful. All right. Well, thank you so much. Let's all give a quick round of applause to Dr. Shewokis for helping us out here.